and send a link to the presentation on the chat.
Yes, I can do that afterwards. I need to like download it and I will post it a little bit later. I don't have it in a format that I can actually send it to you at this point. Yeah, I will do that later.
Thank you, Pratima. Okay, and so I am recording, and thank you for reminding me.
Cool. Quick introduction. I am Pratima Nambiar. I lead the teams that build and operate the Service Mesh and Ingress Gateway platforms at Salesforce. And today I will walk you through, I'll start with setting some context on Service Mesh evolution at Salesforce. And then I'll talk about how we migrated from our in-house control plane to Istio and some of the contributions that we made to Istio in order to enable that. And then I'll talk about some community contributions that are crucial for us at Salesforce to enable us to adopt Istio to solve more use cases that we are very closely watching and also contributing to. And then I will cover how we do Istio upgrades, again, because we are using Istio quite a bit at Salesforce. Upgrades are important, so I'll cover how we do upgrades and then end with some closing thoughts. So first, to set some context, we started to look at how to solve these common problems with service-to-service communication and use service mesh design pattern about 4 or 5 years ago. And we started off with just Java libraries, embedding them in services to solve these problems. Then we moved to a out of process sidecar, like essentially following the mesh design pattern with Linkerd sidecar. And then in, I think around 2017, we migrated to using Envoy because Envoy is more performant. However, at that time, there was no good open source product that we could use as the control plane. And therefore, we started off with an in-house control plane that was bare minimal that would work for our needs to configure the Envoys that we had. And then in 2018, when Istio released its first version, when we looked at it upon initial review, it looked like it was solving some of the same problems that we were trying to solve. Our in-house control plane worked great for us, and in fact, it still runs in some of our production data centers because we haven't fully migrated to Istio. But we were starting to get, a lot of use cases for, let's say, stateful set support, service-specific config that was becoming harder and harder for us to evolve our in-house control plane. So that is why when we looked at Istio in 2018, upon initial review, it looked like a feature-rich control plane that was solving for the same problems that we were trying to solve, and therefore was a good fit. And it also seemed to have a great community that was, that contributing to the product, and therefore we decided to do a POC on Istio and then eventually migrated to it. With our adoption with Istio, we first, had to get feature parity with our in-house control plane in order to even think about adopting it. And then in our existing deployments, our intention was, as we were swapping out the control plane, we wanted to keep the customer interface changes minimal so that we could just swap it out without them having to do much. So we brought up both the control planes, the in-house and Istio in these deployments, and then we migrated services gradually. And then in new deployments, we just run with the Istio only mesh platform. Now, for the first part of it, which is to get feature parity with our in-house control plane, this is kind of the high level what it looks like. We used to run our in-house control plane, but now run Istio D, and it serves both Kubernetes services and services that run on bare metal, because our monolith still runs on bare metal. And I'll talk about more of these other components in a little bit. But the one that I highlight here is kind of, I'd like to talk about that a little bit to start with. When we wanted to do the POC, we ran into our first blocker with using Istio, which was that at that time in 2018, Istio worked with Citadel for certificates and did not support an internal CA or a custom CA. And at Salesforce, we are required to use our internal CA for certificates, and therefore we had to integrate with that. So that was our first contribution to Istio, which is making MTLS work with a custom CA. And that's what we run in our production data centers today. And this is what it looks like today. It didn't look like this 2 years ago, but this is what it looks like today. Envoy, the Istio proxy, communicates with Pilot Agent via a secret discovery service API, so an SDS API. And Pilot Agent then reads the certs from the file-mounted or in-memory volume-mounted certs rather than from Istio-D or Citadel. And we have a custom cert refresher that is Salesforce specific that we run in our Kubernetes clusters that refreshes these certs. So we're able to get, custom certs provisioned by our custom CA work with Envoy for MTLS. So this is what it looks like from a config perspective. If you want to understand what the configuration is, you can configure the Istio proxy to say you want to use file-mounted certs, and then point to the actual location of the directory where you've mounted these certs, both the client and the server-side certs. And then Istio does the magic, and the proxy actually does the magic of ensuring that hot reload of certs happen when the certs gets refreshed, and there's no interruption to traffic. So this is our first contribution to Istio, which not only did we do that first, PR to actually make it work, but over time, as Istio's sort of the features related to MTLS and how we manage certs changed, we have evolved this custom CA integration so that we can ensure that it continues to work for us. So we were involved with the pre-SDS implementation. We added integration tests to ensure that this integration with our custom CA will not break. And then when we switched to the SDS implementation, we made changes there so that as it evolves, this feature continues to work. As you can see, it's one of the fundamental features that we would expect out of the mesh platform. So it's crucial for us. Moving on, coming back to that diagram that we were looking at earlier, our in-house control plane publishes metrics. So essentially, the proxies publish metrics to a metrics service. Envoy, it has a metrics service API that our metrics relay service implements, and then it transforms or filters out metrics before it publishes them to our metrics platform. With the intention that our service owners should not have any change in their interface and how they observe traffic when we switch from in-house to Istio, we had to make certain changes. Istio at that time, a couple of years ago, would only publish metrics via Mixer, and it sort of aggregates metrics and does not let you publish more lower level telemetry. We enhanced that so that we could publish more lower level Envoy telemetry. And we did a couple of things there. So we made the metrics service be configurable. So as you can see, you can configure the proxies to point to a particular metric service if you want. And that communication also uses MTLS, so you can configure TLS for it. And we also made some enhancements to publish these metrics using an alias so that we could maintain the metrics queries that our service owners were using. We could maintain that, and so they didn't have to change their metrics and alerting that they were used to. Coming back to that diagram there, let's talk a little bit about this config webhook. With our in-house control plane, we were applying some default config to all the services. For example, we have a resiliency framework, a testing framework that runs through some common scenarios like rolling upgrades, crashes of services, transient failures, and we tweaked the resilience policies of the proxy to maximize the success rate of requests when these issues happen. And then we apply those resilience policies using our in-house control plane. Now, when we switch to Istio, as you're probably aware, Istio allows you to configure these things using Istio API at a per service level. So you can define virtual service and destination rules per service. And we didn't want to expose that to our service owners because they are just used to just running the proxy and then getting mesh capabilities. So what we did was we had this config webhook automatically generate the virtual service and destination rules. But then we hit a point where we couldn't apply those resilience policies because they were not exposed as Istio API. So the next set of, so our next set of improvements were related to, well, you know what? I think I missed, hold on, let me go back. So our next set of improvements were related to being able to apply these resilience policies via the Istio API. And we did this in two ways. In some cases, these resilience policies, it made sense to make them the default in the Istio product. So we discussed it with the community and we said, yes, for HTTP, these retry codes, we should retry by default. And we made those the default and contributed back to make those the default in the product. And in some cases, it made sense to expose it as Istio API. And so we enhanced the Istio API, for example, to configure TCP keep alive attributes, to configure some retry configuration and stuff like that, so that we can then use that API and apply it via our config webhook. This again was important for us so that our service, firstly, we had to be able to apply these resilience policies. And two, we didn't want our service owners to worry about it. So we used the config webhook to apply it. Let's look at that next highlighted section there. As I mentioned before, our monolith runs on bare metal, and we onboard those bare metal services onto Istio. So we run Istio proxy next to it, and then it talks to the control plane in Kubernetes. However, in order for this bare metal service to participate in the mesh, we continue to use Zookeeper for announcements as a service registry for these bare metal services. And we have a sync service that creates a service entry object. Now, a service entry object is an Istio CRD, an Istio API again, that allows these services that are not running on Kubernetes to participate in the mesh, just like as if they were a Kubernetes service. So we created these service entry objects via the sync service into and created them in Kubernetes. Now, when we did that, we noticed that the control plane wasn't as performant. We had a ton of different service entry objects, and the control plane wasn't fast enough in processing these requests. We saw issues with availability of the control plane. So we made improvements to the control plane in how it processes these service entry objects. And in general, we've made changes to improve the performance of config generation. As you may already be aware, Istio takes the Kubernetes service objects, it takes the Istio configuration, the CRDs that you create, and then it processes them and converts them into Envoy config. So within that config generation process logic, we made some performance improvements over time so that it is efficient. Some other contributions that are worth calling out, especially as we were running in production, is one, when Istio, when Kubernetes gets a a shutdown signal, it sends a SIG term to a pod, and Istio proxy is shutting down, it wasn't triggering the listener draining process. So we made changes to the product so that it does now trigger the listener draining process, so that incoming requests are stopped and we process any any requests that we already have are processed before the proxy is shut down. We also enabled the configuration of Redis services. So we have Redis services that run on mesh at Salesforce. So we enabled configuration of Redis services using Istio. We also made some changes to the sidecar CRD and how that is processed. So the sidecar CRD allows us to configure the listeners at a proxy, and we made some changes to how the clusters are created based on that information. So we're reducing the number of clusters to only what's required for that Envoy using the sidecar CRD. And more recently, we've adopted, the new feature of Istio, which is intercepting DNS requests, or the DNS proxy feature. We made some enhancements to that. We use it for cross-cluster communication. So if there's this client that's running on one Kubernetes cluster and the service that's running on another cluster, and they're communicating via TCP, we need the DNS. The proxy can capture DNS requests and then resolve those requests locally rather than sending it to a DNS server. And so we are able to use this feature to resolve DNS requests of that remote service and support a mesh that spans multiple Kubernetes clusters. Some other community contributions that I would like to call out that we either made some changes to, or we actually rely on, the communities, these big changes that the community, or big features that the community is making to the product for adoption of Istio at Salesforce. Good example of where, our bet to use Istio paid off was when Envoy deprecated the V2 XDS API, and we had to switch to the V3 API. With our in-house control plane, we would have had to refactor our in-house control plane to support V3. Otherwise, it would be incompatible with newer versions of Envoy. But however, in deployments where we use Istio, we are just able to rely on the community's effort to do this migration, and that has helped us immensely in production. A quick note about Envoy Filters. So again, Envoy Filter is a CRD, an API that Istio provides that allows you to modify the Envoy config that the control plane generates. So you're able to make more fine-grained changes directly to the Envoy config without making an Istio API change. And we've used the Envoy filter in some cases. It has helped us sort of try out Envoy config that's not yet exposed by Istio API, maybe to see if it's even a good thing to make that change. We run some tests, we are comfortable with the change, and then we take that to the community and figure out how to expose that feature as an Istio API. So rather than first make the Istio API, in which case we have to be very careful about how you expose it via the Istio API. Instead, we try out the change directly with Envoy config. We get good confidence in what the change is, and then we take it to the Istio community and make those changes. So the Envoy filters has definitely helped us sort of adopt a service mesh for a variety of use cases. But I will talk about one of the side effects of using Envoy filter, especially when you have to do upgrades in a little bit. Stateful set support is another sort of broad area that we are really thankful for all the contributions from the community. We are adopting mesh for a ton of different stateful set type use cases. And this support has definitely helped us. We've also contributed a few changes related to this as we have adopted Istio for these use cases at Salesforce. I talked about multi-cluster mesh a little while back. Essentially, when I say multi-cluster mesh, what we at Salesforce are looking for is within the same network boundary, we might run multiple Kubernetes clusters with different services there for a variety of reasons, but the mesh platform that's on top of it should function and should abstract the fact that we run on multiple Kubernetes clusters so that a service that's running on one cluster can communicate with a service running on another cluster, and it's no different from if they were running on the same cluster. So that's what we're looking for, and we've adopted the multi-cluster mesh features of Istio to make that happen. Another feature that we haven't adopted yet, but it will be very beneficial to us, is the auto registration feature for bare metal services and VMs. As I mentioned before, we run that Zookeeper instance and that sync service for bare metal services in order for them to participate in the mesh. But with the auto registration, we're able to get rid of that Zookeeper. So we have done some spikes, but we haven't actually rolled it out to production as yet. We are in the process of doing that. Again, the WebAssembly extension support, which is essentially running custom code and dropping that into the data plane or onto an Envoy, running Envoy to add custom business logic. We are using it in a couple of cases, but we expect to use more of it as we solve for more different types of business use cases. And some scale-related enhancements. So as I talked about some performance-related fixes that we have done, and that will continue to happen, but there are also some scale-related enhancements that are being made within the community. An example is improving the efficiency of the config delivery between the Envoy and the control plane Istio by using the Delta XDS API. That will be beneficial for us as our mesh grows. Moving on to how we do upgrades, we use the operator flow, the Istio operator flow for doing upgrades. We use Spinnaker at Salesforce as our deployment pipeline. And we use Helm to define these operator CRDs and in general to configure Kubernetes objects and use our pipelines to deploy them. Before I talk about how we upgrade, just setting some context here. So as I mentioned, we use the operator flow. We also have several different environments that we propagate upgrades through before we actually upgrade our staging and our production environment. So we have a few environments before that. And we have alerting in place in each of these environments using the Istio telemetry. The control plane actually generates a ton of telemetry related to config generation or any errors related to config generation, etc. So we alert on those. We also alert on Envoy telemetry to see, to monitor the health and the performance of the mesh. And this is what our setup looks like and how we use the operator CRD in our Canary Kubernetes cluster, and I'll talk about that in a little bit. In our Canary Kubernetes cluster, and essentially the very first cluster that we do the upgrade in, we create an Istio operator CRD and deploy a Canary version of the control plane to a special namespace called the Canary namespace. And then we also create another Istio CRD and deploy the control plane to the main namespace, the control plane namespace. And then we use the Istio CRD to create the Ingress gateway in the Ingress namespace. And in the Canary Kubernetes cluster, which is the very first cluster that we attempt the upgrade in, we first upgrade the Canary control plane. And we have some sample services that we communicate that communicates with this Canary control plane, and we run some tests. We rely on the alerts that we have to ensure that everything's okay. And then we validate additional types of use cases using the Canary control plane. And then once we are ready with that basic validation, we upgrade the primary control plane in that Kubernetes cluster. And then we do a rolling restart of all the services that are running there by namespace, and watch for any alerts, integration test failures, etc. And then finally, we upgrade the ingress gateway. We let the this version bake in the Canary Kubernetes cluster for a while. And once we determine we're good with propagating it to additional higher level environments, we then do an in-place upgrade. So we upgrade the primary control plane in that Kubernetes cluster, we validate with sample services, and then we either initiate a rolling restart of the services, or we let the services restart on their own to get the new proxy injected. And then we upgrade the ingress gateway. So, and as I mentioned before, we're continuing to monitor all of these environments. So we let it bake in these, in these higher level environments for a bit before we propagate them further and eventually deploy to staging and production. As I mentioned before, I actually should go back to this diagram here. As I mentioned before, we use Envoy filters for certain types of configuration. And in some, we've not had too many issues with this upgrade, but one issue that we have seen that we're hoping to do something about is the Envoy filter sometimes becomes incompatible with the control plane. And we've seen issues where those error out. So we're hoping to fix that soon. The Envoy filters have a proxy version that you can tie them to. So that's potentially one way we might look to fix it. So we haven't taken action on this as yet, but that's one of the ways we hope to fix it. And maybe a couple of times we've run into some bugs. When we do run into those bugs, when we are validating the, or sort of getting ready to qualify this version of Istio, if we run into bugs here, we go back, fix it in the open source product, we bring it back to the Canary cluster, and then and only then will be propagated forward. So we do, this first deployment in this Canary cluster, we do a lot of validation before we actually, propagate it further. Let's see, I think that's all I had for today. I think we've come a long way in our journey to adopt mesh and specifically Istio. We still have a long way to go. A couple of years ago, when we started off, sending that first PR to the Istio open source product, it was a little rocky. It took a little while for it to be looked at and for it to be checked in. But since then, we've had, a great experience with making changes to the product. We've had very good responses from community members for PRs that we send. Great discussion, and before it actually gets checked in pretty quickly. Also, as we're adopting Istio for a variety of more complex use cases, we've had, we've been able to rely on the expertise of the community to try different things to solve those problems in how we use the product. Or in some cases, if we find a gap, we've been able to come to consensus on how to fix it in the product. And then we send that back as a PR, and it gets approved and becomes part of the product. We've also had, great experience with the feedback that we give in user groups and working groups is heard, and it is used to shape the roadmap of the product. If you look at all the past few releases of Istio, some very relevant features have been added that are important for us as we adopt Istio for more use cases. So thank you very much. I hope this was helpful. Please come and join the community. We would love to have more people contribute to the product. And yeah, thank you.